This video is on functional volume. So these are the types of questions that you sometimes see at GCSE, where you might have like a pool or something, and you're talking about maybe filling it up and finding the height of the water level, or how long it takes to actually fill up the pool completely. So I'm going to do a few questions like this that I found on previous papers to try and maybe help you get a better understanding of them. Okay, so the first thing you want to do in any of these types of questions is find the volume of whatever compound shape you're given. Now, this one here is just a trapezium, okay, and it's been like stretched back, okay. So to find the volume of this, it's just A plus B, this here being 0.5, divided by 2 times by the height backwards. So, yeah, sorry, no, divide multiplied by this height 2 here, and then multiply it back by 1 to get the volume. So we're finding the area of this front trapezium here first, okay. And then we're multiplying it by 1 backwards to get the full volume. Another way that you could have done that is if you could have just drawn a line from here to here, okay, and said that that height there is 1.3 take away 0.5, and then found the area of that bottom triangle and then the area of this top rectangle to find the full volume. It's the same either way. Okay, this gives us a total volume of 9/5 meters cubed. And we're told that the pond has already been like some water has already been removed from it, and the depth of that water that's already been removed from it once being completely full is 20 centimeters. Okay, so 20 centimeters or 0.2 meters, okay, is just like this is where the water level is right now, because after half an hour we've already drained the water and it's moved down by this level. Now the problem with this is that this is just in say centimeters or meters. It's not in unit volume. Okay, so it's not in meters cubed or centimeters cubed or something like that, and that doesn't help us if it's just like this. So we need to convert it into meters cubed. Now we can do that very easily. Okay, and we can do that by saying this is 0.2 or 1/5 multiplied by 2 multiplied by 1. That's the total volume that's already been displaced. Okay, and that gives us this here. So 0.2 times 2 times 1. Okay, now our original volume, take away this one, so take away this what's already been removed, will give us the volume left, which is 7/5 meters cubed, or 1.4. Okay, and this here, because that's the water that we've already displaced after removed after 30 minutes, we can say that this here, 2/5 meters cubed, is removed every half an hour. Okay, now we want to go from removing this much water to removing 7/5. Okay, because this is how much volume is left. So we need to have removed this water, which we've already done, and then remove a further 7/5. So how do we get from removing this much water to this much water? And the time doesn't matter for now. Okay, so we'll call like the multiplier to get from here to here x. Okay, so we're saying 2/5. That's like to do with this down here. So 2/5 meters cubed per hour. Like if we're removing 2/5 meters cubed, okay, x is like how much more. X is the multiplier. How many times we need to do this to get to here. Okay, so rearrange for x, you'll get 7/2. So we're saying that if we multiply this by 7/2, we'll get to this. Okay, but that means because these are both related, that means we also have to times this by 7/2. Okay, so this half an hour times by 7/2 will give us 7/4. So it takes 7/4 hours to complete the next 7/5 meters cubed. This is the same as saying 1 and 3/4 hours, and this is just 1 hour and 45 minutes. We've got this shape here. We've got a cylinder and a cone under it, and we're told first of all it starts off as empty, and then it's filled with grain at a constant rate. Okay, so like I said, just find the volume. We've got pi r squared h for the volume of this cylinder. Okay, and then we've also got plus the volume of this cone here, which is a third pi r squared h. The radius of it is also 3, and then the h is 4 here. Okay, this h here we've just called h, but that's fine. And that gives us a total volume as this, and if you choose to factorize it, you'll get this. Okay, and we're told after 5 hours, the grain is 6 meters above the vertex. So this is the vertex here. We've moved it 4 meters to get to the top of the cone. plus another 2 meters. We'll call that another 2 meters just like up to here. Okay, and this has a height of 2, because if this full thing is 6, it's 6 take away 4. Okay, so the volume that's being removed after 5 hours is this volume here, right? Plus the volume of the kern. Sorry, the amount of volume that's like being filled in. Okay, now the volume of this here, this like smaller cylinder here, is going to be pi r squared, okay, times by this height here, because this is just a small cylinder. And then it's add the volume of this kern, and this volume of this kern is just a third pi r squared h, which is going to simplify to 12 pi, which we've already seen. Okay, and this is how much volume has been added into it after 5 hours. Okay, that simplifies to 30 pi. So 30 pi meters cubed per 5 hours, or 6 pi meters cubed per hour. Okay, after 9 hours, we're told that the container is full. Okay, so if we times this by 9 to get 54 meters cubed, that's for 9 hours. So that is the total volume basically. But we already know what the total volume is. And because these two represent the same thing, we can just make them equal to each other, expand a little bit, and then just rearrange for h to get 14 over 3 meters. We've got this container here with these lengths. And we're told that we drop some like spherical ball into it, and it has a radius 3.5. It sinks to the bottom, and it causes the water level to rise by a little bit, obviously. Okay, now the total volume, remember, just always calculate total volume, is just going to be 12 times 11 times by 10, which is 1,210, and it's centimeters cubed. Don't forget your units. Okay, the height of the water so far is going up 8 meters. Okay, so it's only 8 meters up because you see it's not reached the top. Okay, so 12 times by 11 times this new height 8 is how much is filled, which is 1,056. Okay, now the volume of the sphere, okay, is just going to be 4/3 pi r cubed. Okay, and we drop that into it. Okay, so the new volume after we've put in the sphere is this 1056 plus the volume of the sphere that we've just added into it. Okay, and that gives us something roughly like this. Okay, now we're saying, what is the new height of the water? Well, we know what the new volume is. We know how much is filled up, and that's just this. Okay, it turns out this calculating this total volume wasn't actually helpful, but you know, it's just always good to get a starting point. Now, how do we've got what the total volume is. Okay, now another way that we can express this total volume filled so far is 12 times 11 times by some height h. So we'll just call the new height h, and h represents the volume of the water we're already in with the sphere in it. Okay, so 12 times 11 is 121, 121 times h is 121h, and that equals the new volume. So the new height is going to be 10.21 after we've put the ball in. Okay, we want the rise in the water level, so it's going to be 10.21 take away 8, which is 2.21 centimeters. Okay, we've got this swimming pool here. I think this is the second to last question. We've got this swimming pool here. It starts off as empty, and then it's filled at a rate of 50 liters per minute. Okay, remember, calculate volume again. I'm going to do this one in a different way to the other one I did, just to show, you know, the multiple ways that you can do this. So we'll just draw a line across here, and then we'll find the area, the volume of, say, this rectangle here, and then this triangle that gets like dragged back here. Now, the area, alternatively, you could also just do the area of this shape plus the area of this shape, and then drag that both back by multiplying it by whatever this back length is. Okay, which is just 10 actually. So the area of this top rectangle here is 15 times by 1. Okay, and then the area of this triangle here is going to be 15 take away 6. Okay, so we've got here 9 multiplied by 1, because this is 2 take away 1. So 9 times 1 times a half, because it's half base times height. Half base times height. Okay, and that's the area of this front face here. Now if we multiply that by 10, to get the volume, you'll get 195 meters cubed. And we're told that to get from meters cubed to liters, you need to times by 1,000. So we'll times this by 1,000 to get it into liters. You could have also just divided this by 1,000 to work only in terms of meters if you want. Meters cubed, sorry. Anyways, and we're told we've got 50 liters per minute, and we want to fill up this many meters, this many liters. So if we just do the same thing that we did last time, if we call the multiplier to get from here to here x, so x just represents how many times we have to do this action here to fully fill the pool. Okay, so 50 times by some multiplier x will give us 195,000. This is the same as saying 195,000 divided by 50, obviously, because that's what we're going to do next to calculate x. You'll get it at 3,900. So that means to get from here to here, you need to multiply by 3,900. So to get from 50 to this, multiply by 3,900. But because this is happening every minute, we also need to multiply the minutes by 3,900. So 1 times 3,900 is just 3,900 minutes. And then if we divide that by 60, we can get the time in hours, which is just 65 hours. Okay. Okay, now this question says, which graph best shows the depth of the water? And that's related to this question here that we've just done. Now, if you have a look at this, if you just look through all of them, it makes sense that you'd eventually see a straight line because we're filling at a constant rate. So one of our answers, the answer must have a straight line. So it could be this one, it could be this one because it has a small straight line. Well, it does have a straight line, and it could be this one. It can't be this one though because this is completely curved, and we know that the rate of change of volume is not like variable. It's actually just a constant. Okay, and for something to be a constant, it needs to be the same. It needs to be linear. It needs to be linear. Okay, so it's not going to be D. Okay, could it be A? Well, let's say, okay, so we've got, just look at like the volume, look at the way that this prism is made. Okay, like at the bottom here, everything is very close together. So you'd expect the height of the water to increase very quickly at the beginning. And then when we get to around here, the height is going to increase very slowly because it's got a wider area to first of all fill before it can start moving up to the next layer. Hopefully that makes sense. That tells us that it's not going to have this constant, it's not going to look like this because you don't expect it to increase by the same height each time. Because say here, because it has a less volume to actually cover before it can move to the next height, right? So that means here the water height is going to increase greater than it does here. Okay, so that tells us it's not going to be this one, and it's also not going to be this one because this shows that it's slowing down. This tells us that the depth of the pool, right, is actually increasing more slowly than it was here, which is not true because we've just said the opposite. Okay, and this one here is the only one that makes sense because at the bottom here, the height increases more quickly because it's less volume to fill. And then here, because the volume is greater, so it needs to fill that layer first before it moves on to the next one, and then the next one, and then the next one, all the way to the top. Okay, so this is the correct answer, C. That's everything. Thank you for watching.